Totally forgot what I was going to say in the middle of it, so I stopped talking about it and moved on. So let me finish that discussion that we were doing last time. And it's on page 110 in your Haggerty book, so you might want to look at it because it actually has a good discussion of Pascal's triangle and the binomial expansion. But what we were looking at is how to figure out what the coefficients of a plus b to the n are. So we can think about this problem in a good way, and this is going to help you in terms of thinking about how to figure out stuff like this really fast, because you can't stand to cube anything, right? I mean, nobody likes to do that. Squaring it, you're kind of almost used to because you've done first, outer, inner, last your whole life. But then when you start to get higher powers than that, it's really hard to figure out how to combine these things. But if we think about them as combinations, we can actually calculate these things without having to multiply out stuff. So what we can think about is we have n brackets here, and each term in a plus b to the n is going to choose an a or a b from each of these brackets. So each term is going to have, say, n minus k a's and k b's, because I have to pick one out of every bracket. So every term has n of either n numbers, and there's either some a's or some b's, right? Well, if I count up all the ways to pick k b's out of these n, so there's n of these, right? I just pick k of them to be b's. Then that should tell me how many terms like this there will be, because if I pick that many b's and the rest of them have to be a's, I don't have to pick anything for the a's. Right? So if I pick k of them to pick b's out of, I have to pick a out of the rest, because otherwise there will be more than k b's. Right? So the coefficient for this term is going to be c times c of n to the k, c n k. Where I have n pairs to choose from, and I choose k of them to be b's, and the rest of them are going to end up being a's. So when we look at the triangle, actually the triangle is filled with those numbers. So let me write that down. So the triangle here at the top is, I could pick as few as 0 of them to have b's, right? So if I have 0 of these, if I have a plus b to the 0, I have 0 of them, and I have to pick 0 of them to be b's. So that's the top row. That's the 0 row. In the next row, if I want the a to the n coefficient, I have n n of those terms to multiply together. And if I have a to the n, that means I had 0 b's, right? Then say I put 1 b, so this has to be n minus 1 a's. So out of the n things, I pick one of them to be b's. So this should be the coefficient for that. So all the rows look like this. And then as I go on down, the last term is going to be what? It's going to be c n n, because that would be the b to the n term, right? So across a row, it's going to look like this. C n choose 0 all the way up to c n n. So that's why there's 1s on the sides of the triangle, because there's only one way to choose 0 things, right? And only one way to choose all of them. So that's why the outside of the triangle is always 1s. And in the book, if you remember last time, we said that the triangle looked like this, and that we could add the numbers in front of something to make, it was 1, 1, 1, 1, 2, 1, and that the pairs of numbers would add up to get the number beneath in between those. In the book, there's a proof of why this happens, but you can also prove it. Okay, so what that proof is, it's called Pascal's formula, and it's that CNK plus CN k plus 1, that's two consecutive terms, add up to be Cn plus 1. Choose how many of them. Let's see. If this is the first one, that's the next one. I think it's K. Let me just check it. Yeah. No, it's K plus 1. Let's see. So if this is 2, 2 and 3 add up to be 3. That's right. So it should be K plus 1. Okay, so this is on page 111 of your book, and they have a nice derivation of that. But you should also be able to derive it from the formulas for combinations, which is what? How do I write C and K? What goes on the top?
N minus 1.
N factorial, right? C and K is N factorial because I'm arranging N things. I arrange all N of them, but then I have to subtract
N minus K.
K of them, right? Because I didn't actually pick all of them out. I picked only K of them, and then I divide by K factorial because that's the ways to arrange the ones that I picked, to rearrange them because order doesn't matter. So that should have been equal to PNK over PKK, and that's how I just derived that. So these ones I circle here, these are PNK, and the K factorial is PKK. So just remember that the first thing that you do is arrange the K things that you picked out, and then you divide by the ways to rearrange those K things. Can I put that back up for a second? This? So here's another example of being able to find coefficients. And this is on page 112 of your Haggerty book, just in case you want to look at it again. So suppose that I have, let's see what coefficients they use. I'll use the same ones as they do, so when you look in there, plus x to the r, sub r, sorry, raised to the n. So suppose I have something like that instead of a plus b to the n. And we want to figure out the coefficients. That's even yuckier, right? We definitely don't really want to do that. So suppose I want to, I have, every term is going to have x1 to some power, right? Let's say p1, x2 to p2 times x3 to p3 times dot, 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 times x to the r times p sub n, right? Because there's n of these, so I have to choose one of those. Actually, it's p sub r. It's really p sub r. And these have to add up to n, right? p1 plus p2 plus p3 plus dot, dot, dot plus p to the r equals n. Because I get to choose one out of all the brackets. So if you think of these as n brackets, like I have the first one, x1 plus dot, dot, dot plus x to the r sub r. And then I repeat that. I have n of those. So when I multiply those, I choose, each term, I choose one of these out of here. I see squinching eyebrows.
Shouldn't the terms, like x1 to the p1, x2 to the p2, shouldn't they have plus signs in between them?
No, they're times. I'm saying these are each of the terms. It's going to be, each of the terms are going to have different powers. Right? The last term will be x sub r to the n.
For any one term.
Any one term is going to have some powers like this.
And for any one term, the powers will add up to n.
That powers add up to n. That's what that's for. So each term is that. There's lots and lots of terms that I don't want to write out. Yes?
So some of the, like, the first term is going to be x
to the 1, and P1 is going to equal n. So
That's
there aren't
right.
going to be any. All the
Some
other
of them
terms
can
are
be
not.
0. That's right. So the first term would be x1 to the n. And the last term would be xr to the n. So and then you'd have a bunch of junk in between that you don't want to calculate. Right?
Right.
So you can actually calculate the coefficient using our combinations, which is really cool. Right? It's very cool that you can do that. So the way to do it is knowing that you have to select this first one, x1, I have to select p1 of them from n brackets, right? So let's see. Can I shift the page? Okay, that's all of it. So here what I actually have is x1 times x1, and there's actually p1 of them. Right? And I actually have p2 x2s, if you write them all out as single terms. And then that same thing all the way up to xr. And there's pr of them. But then there's a total number of n things. So there's a total number of n things, so I have n factorial ways to arrange them, right? Except some of them are the same. So this is kind of like rearranging the letters in Mississippi, right? Because I have n things here, but then some of them are going to be the same. Like the x1s I won't be able to tell apart, and the x2s I won't be able to tell apart, and the xr's I won't be able to tell apart, and so on. So the total number rearranged these is n factorial if all of them were different, right? But then I have to divide out by the number of x1s, the ways to rearrange those, right? The ways to rearrange the x2s. So this is the same kind of problem as the Mississippi problem, but it looks different. And the reason why we have to divide by those is because it didn't matter which order we picked the x1s. So one way I might have picked an x1 from there and an x1 from there, and the second way I may have picked the x1 from the first two. And those would be the same if I picked the x1s, just two of them. If I pick the same number of them, it doesn't matter what order I pick them. So this is a rearrangement problem. So it's really cool that you can actually calculate stuff. So let me give you an example, and we'll figure out what the coefficient is. So one example, and this is example 6.9 in your book. Let's find the coefficient of x cubed, y squared, z to the fourth, n, x plus y plus z to the 9th power. That's 9, not q. So we already said it was going to be the total power, 9 factorial, because we know we're going to have 9 terms, factorial. And then we have to divide by how many x's there are, factorial. And then what?
2.
Divide by the 2 y's and divide by the 4 z's. And if I actually want to see what this number is, I can actually write out these factorials and cross out numbers without having to have a calculator, right? So what I would do is I would divide those two first, because this is equal to 2, right? And this is equal to 6. That's easy. So this is equal to 9 times 8 times 7 times 6 times 5. I know I divided by 4 factorial, and that's over 6 times 2. So I could cross out the 6's, cross out the 8 and 2, and get a 4 there. So it's 9 times 7 times 5 times 4. It's 20, that's 63. And that's 1260? So if you do have to calculate these, which I never require you to do, you can always multiply them out and cancel things. Because sometimes your calculator won't calculate them. So you definitely want to be able to do this. And actually, I highly recommend doing this, even if you don't turn it in on your homework. I recommend doing it just for practice so you remember what factorial means. Because the more you do this, the more you're like, oh, factorial is this, and this factorial over that factorial does blah. So if you practice, you'll be able to recognize how things work.
I'm missing something. Why didn't you take 9 down to 1? We went 9, 8, 7, 6, 5.
Oh, because I was dividing by the 4 factorial. Because that would have been, if I kept going, it would have been times 4, times 3, times 2, times 1, but that's 4 factorial. And it's divided out by that. That's why I went ahead and did that.
Oh, okay. I thought you were going to have a 3, a 2, and a 1 left, but you don't.
No, no.
I see it.
I had a 4 factorial, so I have to divide by 4 factorial, not just by 4.
Okay, I see it.
So you have to be very careful with those factorials, and that's why I recommend practicing. So they have one more example, which is actually kind of cool, because it looks even less like you'd be able to solve it. So the next example is x plus y plus 3 to the 7th, and you want to find the coefficients of x cubed y squared. And of course, before today, you'd be like, are you nuts? I don't feel like doing that, right? You have to raise something to the 7th power and then add up all those terms. But now you can figure it out because we know that we have to arrange 7 things. So first we just treat this 3 like any old other thing. So we have to arrange 7 numbers because we know that every one of them has 7. Then we have to divide by how many 3's are there, right? How many x's are there? There's 3. How many y's are there? There's 2. And then, there's just, what did you put squared? What did you say? Well, if x plus y plus 3 to the 7th has, I have to know how many 3's there's going to be, right?
So it's 7 minus 3 minus 2.
7 minus 3 minus 2?
Because any one term, they're going to add up to 7, right?
If there's 3 of these and 2 of these, the rest of them have to be 3's, right? So that's 5, so 2 of them left have to be 3's. So I have to divide by the number of 3's there are. So the bottom numbers should add up to the top one. Right, 3 and 2 and 2 add up to 7. So that's the total number. So we can figure that out. And that's 7 times 6 times 5 times 4 times 3 factorial all over 3 factorial times 2 factorial 2 factorial. So I can cross out those 3 factorials. Sorry, I'm off the board. Times 4 all over 4. So I can cross out the 4's because that's 2 factorial times 2 factorial is 4. And then it's 7 times 6 times 5, which is 210, right? So it's pretty neat. Like before today, you'd be like, haha, I don't feel like solving that problem. And now it's an easy problem to solve. Yes?
But when the coefficient actually being 210 times 3 squared.
That's right. You're going to have to put that back in because 3 squared is actually part of that term. So it's going to be 210 times 3 squared times x cubed y squared is what the final answer is. Because we have to put the term back in, and we figured out that that had to be a 3 squared right there. So it's actually 9 times that. But since the coefficient combines that 3 in there, that's why we have to do that. So I would definitely try the problems that are in the Haggerty book for counting, because there's lots of them, and they all have answers in the back of the book. So those are definitely worth trying, and your homework assignment will be posted today, tomorrow. Actually, tomorrow it'll be posted by the end of the day tomorrow, so you'll have homework 9, and there'll be plenty of counting problems in there. Let me give you one trick that I like to do when I do counting problems, and that is I like to break them into 2 parts. Now, you've already noticed me doing this before probably, is that I always do things, first I solve for order matters. If I'm trying to figure out the formula. So this is for the formula. Order matters, and then I divide out the order. So that's in figure out the formula. Now the funny thing is actually if I'm doing a problem, I'm going to do the reverse. So like say I'm awarding prizes. And I have 100 tickets that I'm giving out, and this is like one of your homework problems. Say there's 100 lottery tickets. And normally order matters in those problems because lottery tickets you usually have a first place, second place, third, and so on. So, or a raffle or something. You have different things for different tickets that you get drawn. So let's suppose that we have a raffle with 100 tickets. Now, it's easy to do this problem if I just say, okay, there's 4 prizes and I have 100 tickets. How many prizes are there? What's the answer? 4 prizes, 100 tickets. How many ways are there to award the prizes? Order matters, right? So it's a permutation. I have 100 things to choose from, and I choose 4 of them. So the answer is P 104. And if you have to give the formula, it's 100 factorial over 96 factorial, right? Which this answer is acceptable to me. P104. On a separate part of the homework, I'll make you give me this part. So I want you to know both, but on this problem, I just need to know that you know which it is. It's permutations. Okay, so that's not a very hard problem to solve. I just do permutations. But what if I say ticket 49 wins a prize? I didn't say which one, right? So now what do? I have to award 3 more prizes. First I have to choose which one this person gets, and then I have to award all the other prizes. Or, alternatively, we can do the problem like I'd like to do, and that is for me to get all the prize winners up on the stage and then rearrange them by order. That's what I like to do, is get them all together and then rearrange them, because sometimes you're going to have things like this person gets a prize and this person doesn't. So it's a lot easier to say, okay, these are all the possible people that get prizes. So what I'm going to do is I'm going to put 49 here. I know 49 gets a prize. So, and the other, 99 people can get the rest of the prizes, right? So I'm going to choose, so out of that I'm going to choose 1, out of this I'm going to choose 3. So this is, out of one group I'm going to choose 1, out of 99 I'm going to choose 3. So that's the ways to get all the people together, because order didn't matter. I just choose 3 of them in that second group. And then I arrange the 4 prizes. So I've chosen 4 people. I'm going to give out 4 prizes. If you do it like that, you're keeping all your selections separate from your ordering. If you don't keep your selections separate from your ordering, a different thing happens. So you might have answered this problem by this. You might have said, well, there's 99 people and 3 prizes to give out. And then I would have said, no, that's not the answer, because 49 could have got any one of the 4 prizes, right? So there's actually 4 ways to do it. And I don't like answers that look like that. Because what you're doing is you're fixing your answer. Right? This way, the top numbers add up to 100, the bottom numbers add up to 4. So out of the 100 people, I'm choosing 4 people to get prizes, and then I'm arranging them. And so all of my answers can have the same form if I do it like that. So let's solve another one. Let's say that 79 and 47 don't win anything. And 54 and 20 win prizes. How many ways are there? Well, here we can group up our people into 3 separate groups, right? What's going to go in these 3 separate groups?
71, 47 people that don't win anything. Either win something, and the rest of the people are going to get the other 2 prizes.
So the 96 people are here. So here, how many do I choose? 0 for winners, right? Out of here, I choose 2. Out of here, I choose 2. So from C22, I choose, sorry, C20 is the number I choose there. C22 is the number I choose there. C96 2 is the number I choose there. The top numbers add up to 100. The bottom numbers add up to 4. Then I arrange my 4 winners. So you see how now I can just put P44 on all of my solutions, or almost all of them, unless it says like this person wins the grand prize, and then you only have to arrange the other 3, right? So this works because these are disjoint sets, because none of these winners are over here. So you have to do the problem a little bit different if you say, what if we say that out of 1 of 39, 42, and 79 win a prize. So how many ways are there to give the 4 out if that's the case?
What if those 3?
Mm-hmm.
1, 3.
Let's say win the grand prize. And actually the other 2 are allowed to win a prize also, but they might or might not. Then we can't keep the sets from overlapping because these people could win. So out of these 3, I'm going to choose 1 for the grand prize. And then I have to toss 2 of them back in. So out of 99 now, I have to take like 2 of these, right? Toss them back in the selection and choose 3 for the other prizes. So this is 3 things taken 1 at a time, and that's already giving the grand prize. These 99, I choose 3 of them, and I only have to give out 3 prizes, so I do P33. So I multiply all these. And the top numbers don't add up because I put 2 of them back. That's with replacement. That's what that is. So you have to be careful in reading the problem and figure out when there's replacement, when there's not. If there's no replacement, you know the top numbers will add up to 100 and the bottom will add up to 4. So this doesn't mean you can't solve it by doing all permutations and then fixing them. If you are happy doing that, go right away. Go right ahead and do it because they come out the same. So they do come out the same because I could have done P99.3 here and it would have been fine because that's what this is, right? C99.3 times P33, that's exactly equal to P99.3. If you do the formulas, you'll get used to it. So it's sort of automatic for me. Okay, so in a counting problem, the most important thing is to ask yourself what questions? Does order matter? Is there replacement? So let's figure out if order matters. If order matters and there's replacement, what kind of problem is that? It's a permutation because order matters. If there's replacement, then that just means what? Like, what kind of problem is it? I'm allowed to use things I select more than once. So it could be license plate, right? I have this many letters. How many ways are there to make a license plate? If I have 6 letters and they all come from the alphabet A to Z. Right? So these are of the form N to the K. Right? I have K blanks and N choices in each blank because I have replacement. So if order matters and there's no replacement, then that's a regular permutation, right? And that's P n k is equal to n factorial over n minus k factorial. So what's an example of this kind of problem? Yeah, the ways to give out prizes like we just did. Okay, how about if order doesn't matter and there's no replacement? Order doesn't matter, we automatically know that's a combination. If there's no replacement, it's a regular combination, right? Then that means how many ways are there to select 3 people for a photo? And I don't care what order they're in. So that's combinations of n things taken k at a time, which is p n k over p k k. The only funny one is if order doesn't matter, but we're allowed to use things more than once. So those are the divider problems, right? And the only difference between the divider problems and the multi-arrangement problems is that in the multi-arrangement problems we've got, like in a divider problem, we just have things and dividers. In the multi-arrangement problems, we actually have as many different kinds of things as we want. So in the coefficients problem for x1 plus x2 plus dot 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 plus xr all raised to the nth power, I have up to xr different things. So this is a divider problem. And that's combinations of what? Dividers and objects. Choose the objects or the dividers. It doesn't matter which one. And dividers is just what? Kinds minus 1. Right, so if I have 5 kinds, I have 4 dividers. Okay. So those are the 2 questions you have to ask yourself. Does order matter? And do I have replacement or not? And then you might have special things like this person doesn't win a prize or that person does. So you have to actually figure those out and then answer the question. So you don't want to start using formulas until you're sure you know which kind of problem it is and that you've solved it down to a part where you can use one of these formulas. And what's the best thing you can do to make sure you're doing the right kind of problem? Draw a picture. So I highly recommend drawing pictures whenever you are doing accounting problems to make sure that you know what you're doing.
Are you going to give us these formulas on the test?
No.
Okay, so we just have to know them.
You need to know them.
Okay.
And I've taught you how to derive them, so you should be able to do that. And by the time you do the test, you will have done enough problems that it should come naturally.
But it's a take-home. Right?
The test 4 is not a take-home. It's in class. So counting right now, it's not going to be on that. I'll tell you if it will be, but I don't think so. Okay, so let's get started with graph theory. We've already started some graphs before, right? We've been making graphs for what? we made directed graphs for binary relations. So they can be represented by directed graphs. So a general graph just doesn't have a direction on an arrow. So a graph is composed of nodes and edges. So nodes are the circles or dots, and edges are the lines that connect them. And usually the lines do represent some relation or some kind of connection. So like a road going from one thing to another, or a wire in a network going from one thing to another, or something like that. So usually the edges represent some kind of connection, a communication, or transportation, or some kind of moving stuff connection. Or a relationship, like these two people are brothers. So actually a family tree is a graph, right? And the only thing that's different between a family tree and a regular graph is that you have stuff like this. That just doesn't draw the lines directly from two. Actually, you have to have what? You have to have two parents. So this is how they make that relationship, but that's because these relate to two things, right? Mother and a father. So, but they're very, very similar. It's almost the same thing. Okay, so we say we have a simple graph. So I'm just going to give you some definitions. They're in your notes. So they're in the packet. So if you want to turn to the beginning of the graph theory section, they are in there. So a simple graph has no loops. And that means they don't have the reflexive edges like we had in our binary relations graphs. If something was reflexive, it had a loop, had an edge going from itself to itself. And I have to give you some other definitions. A path is typically a listing of vertices. So you can call things nodes or vertices, and a single one is a vertex. I just love my advisor. Whenever he tries to say singular vertices, he says vertice. It's really cute. Anyway, it's a vertex. If we have more than one of them, it's vertices. So a path is a listing of vertices. So if I had this graph right here, A, B, C, and I had arrows like this, then I could list A, B, C as a path. If it's sometimes paths can overlap, like I could use the same edge more than once. So I'm not going to define a path to not use an edge more than once. You could use, so in this graph I could also go A, B, C, B, and that would be a path too. But most of the time I'm going to use path to mean that I start and end at different vertices. So that's the only way I'm going to distinguish between those two. So the start and end are not equal. Because if the start and end are equal, I'm going to call it a cycle. So that's a path where start equals end. And you can also call that a circuit. That means the same thing. So in this particular graph that we have right here, a cycle could be A, B, C, B, A. Is that good? Everybody ready? Good. Okay. So now we're going to define some things that we can do with this. So there's a lot of times a graph will represent things like if you were the postman and you had to take mail to everybody, you could put everybody's house was a vertex and the edges were like streets that connected them. And if you wanted to plan to deliver all the mail, you want to minimize how many times you go to each house, right? Or go down each street. So what you might want to do is figure out something where you visit all the nodes, but not more than once. Or you might also want to figure out something where you visit all the edges. So suppose that all the edges represented all the streets in your city, and you wanted to figure out how to do a street cleaning without cleaning a street more than once, right? So, or you're a salesman and you want to go to this many different cities, but you don't want to actually fly between two cities more than once. So there's lots of problems that we have to solve in graph theory. So let's define the first one to be, if we want to find an Euler circuit in a graph, is one that uses all the edges. And the reason why we're doing this one first is because it's easier. And you can visit a vertex however many times you want. Okay, so what's an Euler circuit in this graph? ABCA, right? So AB would be going down this way. So I think of myself as a little person in here. And A goes to B. And then B goes to A. Sorry, it goes to C, and then C goes to A. And that would be an Euler circuit, because I start and end at the same vertex, and I use all of the edges. If it gets more complicated, the more edges you have, right? And the more vertices. So how would you solve, in general, like if somebody gave you a random graph, how would you do this problem? How did I just do this one?
Drew it out.
I started at a random place, and I went along a random edge, and when I got there, I went somewhere adjacent to that. And I did that until I ran out of vertices. Okay. The only time that's going to give me a problem is, it shouldn't ever give me a problem, really, is unless I somehow get isolated and I can't leave, but I didn't cover all the edges, right? No, we have to use all of them. I could end up at my start point, but I'm allowed to leave again. So let's try to do one for this graph and see how it turns out. Okay? So let's start at a random point. Someone pick one. Okay, we start at A. Where do we want to go? And back to A. But I still have edges to use, right? So now where do I have to go? C. Then B. And then D. Now I used all of them, but it's not a circuit because I didn't start and end at the same place. Now why did that happen? But it is, okay, this is called an Euler path because it uses all the edges, but it starts and ends at different places. So what happened when I got to this point right here? I only had one way to leave A. I needed a way to get back to A. So what I like to think of is whenever I leave, I have to have a way to get back. So I have to have an even number. If I want to get back somewhere, I've got to have an even number of edges going out of it. So if I want to start and end at the same vertex, that one has to have an even number of vertices. Sorry, even number of edges going out of it. And that's called the degree. So degree of a vertex V is equal to the number of edges leaving V. Or touching V, actually. Touching V or leaving V is either way. Because if you have a directed graph, you can have an out degree and an in degree. Out degree would be how many are leaving, and in degree would be how many are coming. But those are kind of intuitive definitions, once you know what a degree is. Out degree counts the out arrows, and in degree counts the in arrows. Leaving V or touching V. Those are two equivalent ways to say it. V being the vertex. See, that's the argument right there. So the degree of A in this graph is 3. Degree of B is 4. Degree of D is 3, and degree of C is 4. Right? Okay, so if I start with B or C, let's find out what happens. So let's try by starting with B. Okay, just call out some numbers or letters.
A.
B.
D.
D. B, C, A, B, D. What else?
C.
C.
B.
I can't go back to B because I already used that one, so I have to use A, right?
So you leave one open.
And now I'm stuck because I didn't use this one, right? So it looks like actually that I need more than just the start vertex being even. I need all of them to be even to get an Euler cycle. Because if you look at this, when I go to something, I have to leave it again. All the time. Including the start one. If I leave it, this is when I leave it, and I have to come back to it at the end if I had an Euler cycle. So every one, when I arrive, I have to be able to leave. So that means I have to pair every one. I have to have one that I go in and one that I go out. So in order to have an Euler circuit, so an Euler circuit exists if and only if all vertices have even degree.
Well, you could have one where just one of those vertices has an odd, couldn't you? Because if you drop that BD connection, we would have a Euler circuit there.
No, because we didn't end up back where we started either.
That's true.
So actually the thing to do would be to connect A and D, and then we would have been okay, because A would then be even and D would be even also. So that would have solved our problems, because we could have gone back to D and then gone back to D from there. So how come we got an Euler path here, but couldn't even get an Euler path there if I started at B? That's right. Because I started with an even one and not one of the odd ones. If I have exactly two odd ones, I'll be able to leave the first odd one and end at this last odd one, at the second odd one. But the rest of them in between have to be even because I have to get there and I have to leave. All the vertices in between have to get there and leave. So it has to be an even number for all the ones in between. And the end ones can be odd. So if I start out with an even one and I've got odd ones in there, I won't be able to get back to it. I won't even be able to finish using all the edges. So in order to have an Euler path, I have to have exactly two. So there exists an Euler path if I have exactly two vertices with odd degree, and the rest are even, right? So an Euler path starts and ends with different ones. They have to be the odd ones. And if that's the case, as long as I start with one of the odd ones, I'll be able to make one. So we pretty much use the algorithm to find the Euler circuit that I'm going to tell you. Like, I'm going to tell you the steps for it. It's called Fleury's algorithm, and it's guaranteed to find any Euler circuit in any graph that has one. So all you have to do if you want to check for Euler circuit is make sure it has all even degrees for all the vertices, and then you can just run Fleury's algorithm on it, which is pretty much what we just did. There's only one thing you have to check for. And you can use the same algorithm as long as you start with the odd degree one. The same algorithm will work to give you Euler paths if you have two odd vertices. So let's talk about Fleury's algorithm right quick. So the first step is to choose a random vertex. And just call it V. Whichever one you chose, call it V. Then choose a random edge connecting V to something else. So VU. And then travel along that edge. And then delete that edge as long as it doesn't disconnect what you have left. The graph that's left. So let me try to make an easy example where I can travel somewhere and leave myself hanging. There's one in your notes. Has anybody got their notes? Oh, there it is. Okay, I'm cheating. There it is. It looks like this. How's it labeled? 1, 2 across the top, and then 3 in the middle, 4, 5 on the bottom?
5 in the middle. 5, 4.
Okay. So that's 1, 2, 5 in the middle, 4 here, and 3 there.
I can't see where I'm pointing. Yes.
Okay, there's a big graph there. So in here, you guys can tell me what order they go. Which one did they pick first?
2 is B.
2 is the first one? Okay, so we pick 2, and then what?
Go to 3 by the outside edge.
Go to 3. So this one's deleted, so I'm actually ignoring it for the rest of this. So now 3 is my vertex, and I have to choose one from there.
Go to 2 from the edge.
Then it goes to 2 again. Then what?
Goes to 1.
It goes to 1. So that's okay because the stuff that's left is still connected. Like the 2 is still left, the 5, and all these are still connected. Okay, then what?
Goes to 5.
And it goes to 5. Is that one still okay? And then what I can't do is go to 2 at this point. Right? Because 2 only has this 1 left that I can use. So that has to be the one I travel back to 2 on. So I'm not allowed to use that one. That's the only thing in Fleury's that you can't do. Okay, so I can't choose 2, so I have to choose 3 or 4. Which one does it choose? It chooses 3. And then what?
To 4.
Now I choose 4. The only other thing I didn't write on there is if that's the last choice I can make. So that disconnects 3, right, when I made that choice. But there's no more edges from 3. So the only other thing is I now delete 3. So the fourth thing is if you have a vertex, you know, as soon as you've removed all the edges, you delete a vertex. So delete a vertex with no edges. Because you've already visited it the maximum number of times. You've already got all of the edges connected to it, so you don't need it in your graph anymore. So now we go back to this problem. We go to 4. Then we don't want to go to 5 because then we have to go to 2. Right? So we don't want to go to 5. We actually want to go to 1. Because if I went to 5, what happens is after I've deleted all of this stuff, I have 1 and I have 2 and I have a line to go into 5. I don't have 3 anymore. I've got a 4 over here and I've got 2 edges like this. Sorry, you guys didn't see that. So here's what I have left when I'm choosing from 4 what to go to next. So I can't go to 5. So I need to go up to 1, back down to 4, and then I can do those 5 and 2, right? So that's what I do. I go up to 1 and back to 4. So here we go. 1, 4. So here's that on that graph. And then 5 and 2 are my last 2 choices. Okay, so most of the time you don't have to think anything tricky. You just go on random edges and basically I don't even think about the rule of like not disconnecting. I just try to go and cover all the edges, and if it messes up, I start over again. Or I undo the last one that I did.
Does this explain why if you get stuck in like a maze, you should put your hand on one side and keep your hand on one side?
Yeah, it's kind of like that. It's like if you get stuck in a maze, you always want to make sure you don't always like keep going back and forth on the same path over and over again. So if you keep your hand on one side and always follow that wall, then you won't be using the same things over. It's kind of like that. Any questions about this? So after you try a few, you'll be really clear about what this disconnecting thing is. Then you won't have to draw a picture. Like in your notes, it's got a picture of like taking out every single edge and checking to see if it's what's left is disconnected. But we sort of have a natural feel. Like, you know, when we had just those 2 left, I knew I had to use the 5, 2 last. And I didn't want to get to 5 before I was ready to finish. Right? So you kind of have a feel for it while you're doing it. So the algorithm writes it down so a computer can do it, which a computer doesn't have a feel for this stuff, right? But you do when you're drawing it, so it's easier for a person to do it. But it's not a hard algorithm to implement either. Because a disconnected graph is what? All I would have to do in an algorithm to check for a disconnected graph is start at a random place and just go to random edges. And if I ever got to a point where I had nowhere left to go, but I still had vertices left I hadn't used, then I would know I had a disconnected graph, right? So that's easy to check, actually, with a computer program. It's just to see if it's disconnected. You just go on a random path, and if you ever get to a point where you can't get to the rest of them, it's disconnected. So that's something I didn't define yet, but it's something almost intuitive. So a connected graph is one where, let's see, there's always a path for all u and v, where u and v are vertices in the graph. There exists a path P that starts with u and ends in v. And that matches with what you should have an intuitive feel for what connected means. Because if it's connected, you should be able to get from any one to any other one. If it's disconnected, there exists a pair that I can't take any path and get from one to the other. So it's the opposite. And a graph can have several connected parts. And those are called components. So when we were doing Hasse diagrams, that was a kind of graph, right? That was the kind of graph with special things. Like it really was a directed graph and all the arrows were going up, but we didn't draw the arrows. And if the whole thing is connected, then it's possible for us to have one minimum or one maximum, right? But if it's disconnected, you know you're not going to have just one, right? So that's one way to tell in Hasse diagram if we have a minimum or a maximum. If it's disconnected, I couldn't possibly have a minimum or a maximum because that's just one minimal or maximal element. But each part is going to have at least one minimal element, at least one maximal element. So we talked also about wanting to have sometimes be able to go through a graph and visit all the vertices no more than once. So we could use the edges as many times as we want, but we really only want to use them once, and we only want to use the vertices exactly once. So that uses a lot less than the edges in a graph, because usually there's way more connections than just connecting one path through the whole thing. That's called a Hamilton circuit. If I want to, and this is the other way to talk about the traveling salesman problem. Do you remember me mentioning that before? And that was an exponential problem, because the only way to figure out whether we had paths that went through all the places you wanted to visit and came back home without visiting anything twice, I had to list all the possible paths and check to see if they were in the graph. So the Hamilton circuit problem is you want to visit all the vertices exactly once, except I want to come back home at the end. So it's a circuit where I visit all the vertices exactly once, but the begin and end one will be listed twice. This is a harder problem, because if there's any problem that you can sort of apply an almost random solution and almost always get the answer, that's not a hard problem, right? I mean, that just took the length of the Fleury's algorithm for Euler circuits was going to be at maximum like the number of edges plus a few mistakes, right? I might have to check for whether the graph was connected a couple of times, which would take a little bit more time, but on average it would only take me the length of all the edges. On average, this one's a factorial problem in the number of vertices. So one possible solution, so even though someone will tell you that this is a hard problem, there is a possible solution, and that is to list all possible circuits and see if any of them work. So let's do that for a problem. Okay, so I have 4 vertices here. So all the possible orderings of those vertices is how many circuits I have, possible circuits that I have. How many is that? We just did counting. This is order matters. I have 4 things. I'm selecting 4 of them. So that's permutations, 4 things taken 4 at a time, which is 4 factorial. Right? So there's 4 factorial possible circuits here, which is 24. I'm not going to list them all. We could actually see pretty easily, since there's not that many edges, we can see which ones might work. Right? So I won't list any that have A, B in them, because I don't want to take up your class time listing all the possible ones. You know how to list them all. So I can also just try things, which is not guaranteed to find a solution. That's why this is called a hard problem, because if I want to guarantee a solution, I have to do an exponential number of checks. Or I might have to do. In the worst case, I have to do an exponential number of checks, because the solution might be the very last one that I check. So this one works, actually, if I go A to D to B to C to A.
It looks like there's only 8 paths.
Right. If you're taking into account which edges actually exist, there's only a certain number of paths. But if I just want to solve the problem in general and I don't know how many edges I have, this is how many solutions there are. And I need to check them. So if you get a big, ugly, hairy graph, you don't actually even want to count how many edges it has. You just want to know what the solution is. Yes?
For the Hamilton circuit, can you have extra paths that you, like edges that you have not gone through?
Yes.
Okay, just as long as you visit each vertex exactly
Right.
once.
So in this graph, I could have had lots of extra stuff in here. That's actually a solution no matter how many more things I add. So that's a Hamilton circuit for this graph too. I do not need or want to use all of the edges. If I use an edge twice, I've actually used the endpoints of that edge more than once. So I can't use an edge twice. I only can use edges once, so I can't actually use all the edges unless the graph itself is just a cycle. So graph itself is called a cycle if it doesn't have any loops and all the vertices are sort of like in a line, in a loop. That's a cycle. Okay, but there are some kinds of things that you can look at and go, there's no Hamilton cycle. And it's very easy to do that for some kinds of things. So in general, it's a hard problem, but for some specific problems, it's not that hard. So I just did one graph that looked kind of like this, but it didn't have a vertex in the middle. This graph has no Hamilton circuit. Why not?
You have to go through.
You know you.
Because that one in the middle, I would have to use twice, right? Because if I want to cover one half of the bow tie, I would have to start at B and end at B, but then I'd have to leave B again and then go cover the other half. And there's just no other way to do it. So the way that I usually figure out whether I have stuff like that is, in a Hamilton cycle, I know that I have to go to every vertex and I have to leave every vertex, right? Because I want to have every vertex in my cycle. So if a vertex has degree 2, I have to use both of the edges that are adjacent to it, because I have to get there and I have to leave on different edges. So if it has degree 2, I know that edge is in the cycle. So I'll mark the ones that have to be in there. So A's edges have to be in there. And so do D's, and so do C's, and E's. Because all those are degree 2. Not B. B has degree 4, right? But these edges had to be added for A, D, C, and E. If you make a cycle with those degree 2 edges that doesn't cover everything, then you won't be able to cover everything with a Hamilton cycle. So if you just look at that half of it, that makes a cycle. That means that I have to use all of these edges in my Hamilton cycle. But if I have a Hamilton cycle, I also need to cover these. And I can't get on this cycle and leave it again without using B twice. So this is what I do. Add the degree 2. So let's say, let's write it in an easy way to understand. For each vertex of degree 2, add its edges to your Hamilton cycle. If these form a subcycle, in other words, a cycle that doesn't cover everything, then there is no Hamilton cycle. By subcycle, I mean a cycle that doesn't cover all the vertices. It doesn't have anything to do with degree 4. It means that it's a cycle but doesn't cover everything. So that's my own word. A subcycle is a cycle within a cycle. And since I'm trying to make a Hamilton cycle, a subcycle would be a subset of the Hamilton cycle. And you can't have any subcycles in a Hamilton cycle. Right?
So then you would have
Not allowed, because I would have, whatever that subcycle was, I'd have to get to it and then leave it. And I can't do that in a Hamilton cycle. So that's why I can't have any subcycles in a Hamilton cycle.
Excuse me. When you say add, it is edges to Hamilton cycle. For example, if we take the subcycle, we take A, B, D.
Okay, A,
For
B, D, A.
vertex A, we have 2 degrees. 2
For
edges.
A has degree 2, so I add AB and I add AD.
Okay.
I'm just drawing which ones are required to be in the Hamilton cycle.
In Hamilton cycle.
So I draw lines to indicate which ones would have to be in it. Right? Because not all the edges get to be in it. Only some of the edges get to be in it, and some of them have to be in it. They have to be in it if the vertex only has degree 2.
Okay.
Right? Because A, I have to get there and I have to leave it. So in order to get there, I have to have one edge, and to leave it, I have to have one edge. And that's why those are required. So I'll go ahead and mark that those are required. If the required ones make a subcycle, then you know you can't have a big cycle. Here's another kind of graph that doesn't have its Hamilton cycle. Why not?
There's only one path.
Because this little wing thing, I can't get out there and get back, right? I have to have degree 2 for all the vertices to have a Hamilton cycle. So no wings allowed. I could have a Hamilton path, right? Where I start at one vertex and end at a different one and cover all the vertices. So this one has a Hamilton path, but no Hamilton cycle. So if you follow those in order that I just listed, A, B, C, D, E, that's a Hamilton path because it covers all the vertices, but it doesn't start and end at the same one. So it doesn't have a Hamilton cycle. So if you're that traveling salesman, you're going to be stuck in E forever. Yeah, and you better hope that you like it there, because you can't leave again. You have to get the airlines to make a flight from E to A so you could go home. Or else you'd have to break down and go back to D and back to A. Okay, so sometimes it's a little confusing. You've just learned two things, one where I have to visit all the edges and one I have to visit all the vertices. So the way I remember them is Hamilton starts with H, and this one is a hard problem to solve, right? And Euler starts with E, and this is an easy problem to solve that needs all the edges. So that's how I remember to tell the difference. E is for edges, H is for hard. Are there any questions? So all of these are in the notes, so take a look over the notes. And this is the most fun part of the class because you just learn the definitions and you just do them. And you get to draw dots and lines on your homework papers, which you don't normally get to do, right? So you can't say that for most classes, that you get to draw dots and lines for your homework. All right, I'll see you next time.